The phenomenon you just saw was water bumping. Bumping is where bubbles vigorously erupt from superheated areas of the solution when being subjected to disruption. Superheating occurs when a liquid is heated past its boiling point, yet does not boil. To further explain the concept of bumping, we will start with the basic concept of boiling. Boiling happens when water molecules have enough energy to spread out, break bonds, and form bubbles. These molecules, after the intermolecular attractions are fully overcome, they collide with the water surface to get into the vapor state. At the vapor state, gaseous molecules will still continue to collide with the surface, bringing them back to the liquid state. The vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid. Equilibrium pressure is when the rate at which water evaporates into vapor is equal to that at which the vapor condenses back into water. When vapor pressure exceeds the external pressure, the water boils. This is because when vapor pressure exceeds external pressure, the vapor inside a bubble has enough pressure to keep the bubble from collapsing. On the contrary, if the external pressure is greater than the vapor pressure, the water molecules forming bubbles will move closer together and eventually change back into liquid water. When this happens, a solution will remain unboiled past its boiling point. Why doesn't bumping happen when we boil water on a stove? To answer this, we have to look at the relationship between the external pressure of a bubble and the bubble's radius. The external pressure of a bubble is inversely proportional to the bubble's radius. In other words, the smaller the bubble's radius, the greater the bubble's external pressure. Under normal circumstances, the radius of a bubble can be as small as 1 micrometer, making the pressure 1.4 times 10 to the power 5 Pascal. That adds to the atmospheric pressure, which is 1 times 10 to the power 5 Pascal. And together they sum up to 2.4 times 10 to the power 5 Pascal of external pressure. However, if the solution is not homogeneous or is disrupted, the radius will be largely greater than 1 micrometer and, in turn, the bubble's external pressure will decrease, causing the solution to boil. When we boil water on a stove, disruption-inducing nucleation sites, formed by turbulent flow creating tiny high and low pressure areas, proliferate the liquid. On the other hand, when water is heated in a microwave, it may remain undisturbed during the heating process so that there are no nucleation sites around which bubbles may form. This also explains why microwaved water suddenly boils when disruption is introduced.